This is going to be quite a technical demonstration of a library that we're developing. It's going to be live in the notebook, so hopefully it's all going to go fairly well. Honestly, I'm not masking the fact that this was last-minute preparation, and I might have only just prepared it this morning. Please bear with me. OK. So in the Metaverse, we're dealing with an awful lot of gridded data. So that's kind of maybe longitude by latitude, by height, by time, by ensemble an awful lot of the time. So we're dealing with pretty big NumPy arrays. And one of the ways that we're trying to make our scientists' life easier is to develop a library which kind of brings together the various file formats that we have to ingest into a common data model that we can then do analysis on and pump out results. So this library is called Iris. And kind of the interface is pretty straightforward. I'm not going to talk about Iris here. But essentially, this is a kind of a sample netcdf file that we might load. It contains 4 variables and an array for each, which is kind of pretty high dimensional. And in order to have any kind of performance from this, we really don't want to have to load, when we load the file, we don't really want to have these arrays, which are just NumPy arrays, in memory. So we needed a tool which allowed us to have arrays bigger than the memory that was available to us, that were efficient and knew how to access the underlying data for what they represent. So once we've got the kind of big array, we need also to be able to index down, reduce the actual size of the arrays without having to get hold of the full, realize the whole array, and just be able to index into subsets. We also have, we get an awful lot of files, and they kind of come together into a bigger array. So we might separate our data by time step, for instance. So we needed to be able to concatenate these arrays efficiently. What we didn't need, which I think is important to note, we don't need ragged arrays, so we have got orthogonal data. It fills a NumPy array. We just need one data type. We typically use floats or integers, but it's constant within the variable that we're talking about. And we don't really need amazing performance. We just need to be able to do the analyses in the first place, because some of these arrays are pretty big, and the tools don't exist for us to be able to produce the analyses. OK, so as I say, there are some tools that already exist and are under development, Blaze being quite an interesting one in that front. But we think they're quite ambitious and not quite ready for the big time just yet. So we did what any kind of self-respecting software engineer would do. We wrote our own library. And the library is called Bigus. And I'm talking about a pretty early version here, so we've got 0.5. This is the development branch. So Bigus, at its heart, implements an array class which expresses an interface that you will be pretty familiar with NumPy arrays. On top of that, it's really simple, by the way. On top of that, we've got a subclass of that array, which is just a container. So we can create Bigus arrays from another array. So in this case, actually, I'm just going to make a NumPy array. And I'm going to pop that into our NumPy array adapter. Okay? And when I print that, it's just an adapter on the original array. It knows its shape, and it knows its data type. It's pretty simple. So you can't read that because of the screen. But basically, the containment concept is really important in Biggest. It allows us to do an awful lot of things that aren't really possible with things like NumPy, where it's quite hard to subclass the ND array. OK. So like NumPy, we can do things like concatenation. And we have an array subclass called linear mosaic. And essentially, the normal NumPy concatenate takes a list of arrays and an axis, and it will join. So I've just got a 700 by 200 here. Join the two together on the axis 0 in this case, and make a 14 by 200. And you can do the same with Biggest using this linear mosaic. It takes a list of arrays, and an axis. But the important thing to note, the really significant difference here between what NumPy does and what Biggest does, is that in order to create that bigger array, NumPy actually has to allocate the memory and copy the two arrays into that memory buffer. What we're doing is we're just containing the original arrays. So there's no copying of memory. It's just smart and knows what it's doing. Again, I could show you that it doesn't really matter what axis we work on. NumPy increases to 700 by 400, so does Biggest. OK. So as well as concatenation type behavior, we've added a stack type behavior. So we've called it a linear mosaic, where essentially, that's not what I was expecting to happen. Oh no, my apologies. So the real benefit there is that we can just make a pretty long list of arrays and stack them together, and instantly we get quite a big array without having to copy memory around. It's pretty neat. So this is what I was actually meant to talk about, the stack. So we can also create a new dimension with an array stack. And that just takes an array of array objects, and it gives us a new dimension. So we've now got 200 by 700 by 200, a 2 by 700 by 200. Again, same properties, no copying needed. OK. So one of the inputs we just saw was a NumPy array, but technically that's not really that useful to us. So one thing we would like to be able to do is pass through other types of array-like objects into our adapter. And in this case, I've got an example of loading a HDF5 file and pulling out a variable called arange, and popping that into the NumPy array adapter. Okay. So my array now knows its size, it knows the data type, but it hasn't actually read the data from the HDF5 file just yet. It's still a reference to the original file. In fact, if you close the file handle, you would never be able to realize this Biggest array because the file's closed. But you can see that the adapter principle is pretty extensible. I should add that HDF5 already, the HDF5 library already has like an array-like thing where you can index into this variable. We're just kind of extending that to be a bit more generic. So one of the beauties is that we don't have to always just combine kind of NumPy adapters and adapters from HDF5. We can join them together. So the bigger array that I had earlier on, which was created from NumPy adapters, so from actual tangible NumPy arrays, I'm going to join that together with the HDF array, and instantly you have, using the same stuff that we had previously, instantly you've got an array which is of a bigger shape, which combines together the data from different sources. Okay. So going back, this array here, I said when you were passing through the HDF5 variable, we're not actually realizing the array. And one of the concepts with biggest is that you have to tell it when you're ready for it to realize these arrays. So you do that with the ndArray method on the object. And that will then go away and essentially create the NumPy array for you. So it's at that point that you're going to need enough memory in order to hold on to this. As you'd kind of expect with arrays and NumPy-like things, you can index these biggest arrays. And it essentially does what you'd expect. And it's pretty smart in that we've just indexed across the seam of two different sources, one from a plain NumPy array and one from a HDF5 variable. It just works. So one of the reasons we're doing this is, A, we don't want to have all of these variables in memory at the same time. But also we have quite a lot of data, pretty big data, which we can't fit into memory. So we've implemented an engine on top of the biggest arrays, which essentially chunks your arrays into smaller components and does the processing on each chunk, and then brings it back together for you into an array. So in order to do that, we've got biggest, mean, and the normal operations. And you'll find that they're pretty quick. And they're quick because they're deferred. As I say, the operations haven't taken place yet. We only have a reference to the original array that we just passed, and context of what operation needs to take place on it. Okay. And as soon as we do the realization, as soon as we call this ndArray in both places, that is when the operation takes place. So here I'm just I'm printing the aggregation before it actually happens, and it knows the shape of the result. So there's some context there about knowing what taking the mean over axis 0 actually means. And then I'm just showing you that the results are identical. Okay. Right. So when we were doing those two operations, we did a mean and standard deviation. In order to calculate those with NumPy in the traditional sense, you would have to iterate over the whole array and do your analysis, and then iterate over the whole array and do the slightly different analysis. But if you've got arrays which maybe are bigger than that can fit in memory, then what you really want to be able to do is, as we're chunking through those blocks, we do the two analyses at the same time. So say you had a length million array, you want to do 10,000, 10,000, 10,000, taking the mean and standard deviation of each as you go along. So in order to do that, we've got this function here, which basically realizes the two aggregation objects, the mean and standard deviation. They were the things that we computed from the arrays. And we can then see that the result from realizing this using the ndArrays function is actually a NumPy array. It's quite hard to show you kind of this doing magical things on a laptop in real time, but it really is chunking your arrays into smaller components, doing the operations, and then aggregating it all back together and giving you results. I should add, we have an engine already which is doing this chunk processing on multiple threads, but the performance we're not going to see massive performance benefit because they're often not CPU bound, they're more I/O bound. Okay. Right. So we have this concept where we can hold arrays which are bigger than that's available in memory. And we can do operations on them. And that's all working. That's fine. But if sometimes you've got a big array and you want to do an aggregation and the result is another big array, which isn't going to fit in memory, then you're going to need to do you're going to have to accept that you're never going to be able to realize that NumPy array into Python. So what we have is some streaming functionality, which uses the chunking operations, but instead of chunking into a NumPy array, we can chunk directly into a HDF5 variable or netcdf variable or anything that allows indexing as you write. So in this case, I'm just opening up a HDF5 file, making a data set, and I'm just saying save that mean aggregator array into this data set. And that'll go away and stream the results. So the original array could be bigger than memory. The result of taking the mean of that bigger array over a certain dimension could be bigger than memory, and this will still function. Right. So I have a small example which I think is interesting but not necessarily that useful, where I'm going to implement my own array-like thing. I'm sorry for everyone who can't see at the bottom of the screen. And essentially, I just implement this class here called TileLoader. And I give it an x, y, z. And these are the numbers that you would use to reference map tiles from OpenStreetMap. For those of you who don't know, OpenStreetMap splits the globe into 2 to the power of the zoom level that you're interested in tiles in the x and in the y. So at zoom level 0, you have 1 tile, and at zoom level 1, you have the globe split into 4 tiles. So you can give it an x, y, z, and what it goes and does is when you index using the getItem interface, it'll go and get hold of that URL and give you a NumPy array for it. Okay. And I can create one of these things. This is just my own object. There's no biggest here just yet. But because my object has a shape, a data type, and a number of dimensions, I can put one of these things into my NumPy array adapter in exactly the same way I did with an actual NumPy array. And the result is my adapter knows its shape and its data type. Okay. So, yeah, I'm going to. I've made one up here actually with x of 15, y of 10, and a zoom level of 5. And if you visualize that, if we realize it into a NumPy array, and we can im show it, and we can see the tile. Okay.
In this case, build doesn't need to read all the file. It can read only part of the file. Getting just a tile.
So it's already OpenStreetMap have already split the image into 2 to the 5 images. So, yeah. But what we can do is we can, it's fairly complex, but basically make one of these tile loaders for the 2 to the z tiles in the x direction, making a NumPy array. I'm making a list of those. And then I join those together using the linear mosaic. So essentially, I'm going in the y direction here. Essentially, I'm building a column of all the images for a particular x. and then as I'm going along, I'm storing the columns, and I'm joining them together again with a linear mosaic. So I have this really long X, and I have produced lots of them, and now I'm joining them back together again. And the result is an array, a biggest array. So I'm just making the Z9 tiles here. And the array that ensues is a 130 by 130 by 3. And if I'm not mistaken, I think that's about 48 gigs. So way bigger than this MacBook Air can fit, that's for sure. OK. So what can we do with that? That array is just a biggest array, and so we can index it. And these pretty large indices here allow us to make a smaller image from this huge data set. And again, I'm just realizing it and showing it with ImShow. And I've got printouts here to show you which tiles it's receiving or downloading. And you can see it's never actually having to realize the bigger array. It's just getting hold of the subcomponents, the smaller arrays that it actually needs to get hold of. And we can end up visualizing this 58 gigabyte array. I have an interactive version of this, which I haven't put into the slideshow, but I think I linked to it. Is that right? Yep. So in this address, there's a demonstration of this use case, and there's an interactive visualization where you can drag the image around, and it will load the appropriate tiles as you drag it. It's quite an example. OK, that's all I wanted to show you about Biggest. In summary, really, we've implemented an array class. And crucially, in my opinion, the array class is flexible enough to be able to implement an array container, which gives us the power to hold on to a NumPy array, or a HDF5 variable, or a netcdf variable, or just some random object that you can create yourself, so long as it's got indexing functionality. And once you've got hold of that array, they can be easily indexed, concatenated, joined together, and aggregated in an efficient way. And the aggregations can be streamed directly to disk and essentially reduce the requirement on large amounts of memory. As a result, we can define arrays of arbitrary size. I defined one there that was 58 gigabytes, 48 gigabytes. But conceptually, there's no reason why we couldn't have arrays which have infinite length, potentially, or at least any length that you so wish. Obviously, you're never going to be able to realize that in your memory, but you can work with it. You can index into it. You can even do aggregations over it. Yeah, and as a result of our chunk-wise processing, we can operate comfortably on arrays far bigger than can be fit in memory. So it's pretty early on. We're still at 0.5, 0.4 release, actually. So we've still got a lot to do. We've got to flesh out some ideas that this powerful concept of containment gives us. And we think there's an awful lot more to be done with the chunking processing engine in the background. But essentially, the array interface that we've defined is really simple, but pretty complete. I should say, Biggest is not particularly complex. It's like 1,200 lines of Python code. I encourage you to have a look if you're interested. So we're pretty excited about it. I think it's something that could really help the community, particularly when dealing with high-dimensional data arrays. And yeah, I'm happy to answer any questions you might have.